recording.
Do I have to put here anything? Do I have to put here?
No, if you prefer, you see that microphone on the desk?
Oh, okay.
That's on, and that's a little bit easier, but if you walk around, you have to use the other one.
Okay, thank you. I like to be not static.
And make sure the switch is on.
Yes, it's on. But I don't see here the transparency that I put. Oh, okay.
There they are.
Are we on?
Yes, it's recording.
Good afternoon. So this actually, I'm offering 3 courses at the same time. One is mechanical vibrations, that is a graduate course in mechanical engineering. Then undergraduate course in mechanical engineering, which is vibration synthesis. And ocean structural dynamics, that is for ocean engineering students. Some of you are taking it by feats, others are present here. I'm present here. My name is Isaac Elishakoff, and I will give you the information about me. I'm in room 106, old engineering building. That is opposite the library, and that is located in mechanical engineering department. And then telephone number is 561-297-2729. Fax number is at the end 2825. Then email ELISHAKO at fau.edu, and then you can find me on Google if I'm not in my office. And then website. I think HTTP www.fau.edu, I think ENG, FAU.edu, faculty, Elishakoff, HTML. Now this course will be conducted as follows. We are interested, of course, with the grading policy. So there will be homeworks, which are 20% of the grade. Then there will be 2 tests, 2 times 30% of the grade, which makes 60% total. That, and final test, final exam, will be take-home exam. And that is 20% of the grade. So that is how we are planning to proceed. And now we would like to see the syllabus And next time I will distribute to you the syllabus. Actually, also, the textbook is written here. The textbook is called Vibration Problems in Engineering by Weaver and Timoshenko, produced by John Wiley. But actually, I'm not recommending to purchase any textbook. I would like that we stick with the lecture notes themselves. Okay? I will be assigning homeworks here, and you will be. I do not demand any textbook you to purchase. However, if you would like to have any textbook, then naturally I'm not against of getting any textbook. And there are many. I will give you the names of various books that one may get if one is interested. So what we talk about goals, our goals will be in-depth presentation of mathematical techniques for the analysis of continuous vibratory systems. Continuous means not lumped systems of 1 degree of freedom or 2 degree of freedom, but rather to go to the extreme of infinite degree of freedom systems, means beams, plates, etc. Because usually we never see in real life situation 1 degree of freedom system or 2 degrees of freedom system. We see beams or plates, etc., and we would like to analyze them. Now, this does not mean that analysis of infinite degree of freedom system is more complex than analysis of lower number of degrees of freedom system. But we would like not to deal with approximations, but to deal with the system itself as is. So I will give you just very short review. We are probably not going to cover everything that is written here, but first there will be not a review, but free and forced vibrations. There should be D here, forced vibrations of single degree of freedom linear system, frequency response, impulse response, and transform relationships. So the review of multi-degree of freedom linear systems. Multi means n degree. N is any arbitrary positive number. Then we talk about, as we said, structures. Longitudinal vibrations means vibrations of the beams that are in direction of the axis, say vibrations like this, in this direction. Then there could be vibrations, transverse vibrations, when vibrations are perpendicular to the axis, so that is bending vibrations of the beam. Then there are various, okay, so this could actually occupy entire course, just topic number 3 or 1, 2, 3 together. So then we will talk about plates. Plates are two-dimensional objects, like this paper that I'm showing to you is a two-dimensional object because it has actually 2 dimensions that are commensurable with each other. These 2 dimensions are of the same order of magnitude. In the beam, one of the dimensions, length, is much greater than 2 other dimensions. These are in the cross-sectional area. So this is what beam is or bar is. Plates. Here there are some, it turns out that short systems cannot be analyzed by the same theory as longer systems. So when length is big, it turns out that analysis is one type, and when length is small, analysis is of a different kind. Why that happens? Because when length is large, it is larger than other 2 dimensions, and we may possibly neglect something that is small. However, when beam is short, then its length is not much bigger than dimensions of the cross-sectional area. So therefore, these areas cannot be neglected. This is acts like a massive body. For example, very recently, it was found that long carbon nanotubes have the same negative health effects on the people as asbestos. Therefore, it is necessary to consider and implement only short carbon nanotubes. Even long carbon nanotubes, of course, are very, very short, but we are talking in comparison with the cross-sectional area. Now, it turns out that short systems should be analyzed by some other theories. One of them is so-called Timoshenko beam theory. Timoshenko beam theory is very different than the beam theory that we studied in the university. But don't be afraid, everything is just modeling, and we will be just dealing with more complex models than usually. Then there is something, the following consideration. Dangers usually in a system occur in some critical locations. It is not that, for example, when we talk about failure of the airplane, it is not that everywhere the stresses have reached its level and therefore there is a disintegration. Usually it happens in some critical locations where the stresses are achieving the maximum level. It turns out that there is something that is called edge effect. So what we are interested in is what happens at the edges of the system, say clamped edge or free edge or somewhere else. It turns out that action takes place there in some boundaries, because in the boundaries there are interconnections with other bodies, and therefore something could happen there. So we better start there before proceeding further. Then these are all exact methods, what we talked about. But as we know, system may have characteristics that change from one point to another point. For example, modulus of elasticity can change across the axis of the beam. Why this could happen? That is why systems are designed nowadays. In 1991, relatively recently, in Japan, they developed something that is called functionally graded materials. Functionally graded materials are materials that are having varying modulus of elasticity according to our desires. What does that mean? That means that we would like the system to have given properties. I would like the system to behave as I want. So that is like you are going to a tailor and you are ordering something slacks to be done for you, prepared for you, according to your specifications. We can also make materials exactly like that. The same happens on nano level. We can put atoms exactly as we wish to get a property that we wish. So that is called vibration tailoring or buckling tailoring, etc. So actually, we may become a bit of tailors here. So at the end, you will get a certificate. You passed vibrations course, and you are now a certified tailor in vibrations. Then there are approximate methods, and these approximate methods are those developed by some Rayleigh, that is a gentleman from England, Rayleigh-Ritz is from Germany, Galerkin from Russia. These are some methods, powerful methods of approximation that are not giving exact answer because they are approximate, but they give damn good answers to extremely many questions. Okay, and there are some other topics that we would like to cover. So at least I will give you some books, a list of books that could be of interest. So it is understood that one of the best books in the market for already 50 years is this first book by Weaver from Stanford, Timoshenko and Young, all of them are from Stanford. Vibration Problems in Engineering. Okay? If you are in excess of money and you want to spend money, then maybe I would recommend that you buy this book, if at all. Then there is some nice books. Thomson, Theory of Vibrations with Applications. Another good book, Tse and Morse and Hinkle, Mechanical Vibrations. So first is Weaver, Timoshenko, Young. Second, W.T. Thomson. Then Tse, Morse, Hinkle. Then this book is Meyrovich, Elements of Vibrations. Yes, it is 1975, but I think there is a recent edition, 2000 something. Very nice book also. Those who like very small things, Warburton, like a paperback, like a, like Agatha Christie type of approach. So G.W. Warburton, The Dynamical Behavior of Structures, Pergamon Press. Now, there is another book. There are actually many books, but S.S. Rao, Mechanical Vibrations. He's from University of Miami. Dan Inman, also Mechanical Vibrations. This is now very used book. And other books. There are many books available. These are more modern books. There is Maghreb, Balakrishnan, et al., etc. If you did not write, I may leave it still. Now, problems, there is a nice book by Seto, S-E-T-O, Schaum series, McGraw-Hill, called Mechanical Vibrations. It contains problems and solutions. Only problems and solutions. That is nice. I would personally recommend, if someone wants to have it, then first book and the last one. So then first is a text. I mean, one could use some as first approximation of the text, or any book actually can be used. And then Seto is problems. It's nice to have problems and to see how they are solved, etc. So we would like to talk first of all what is vibrations. So naturally, vibrations has to do some with dynamics, dynamical behavior of the system. That means not a constancy in time, but variation in time. Something, some quantity, for example, W of t. W of t can be a displacement of a point in the airplane or in the car or in the ship or anywhere. So I'm interested what happens with the displacement at this point in time. So I just fix the point. So we are not writing where this point is. I chose any point in the system. And I'm interested only what happens with time-wise variation of this quantity. Okay? So that is my main concern. So I may see various kinds of behavior. For example, I could see behavior like this. Look, please. I could see behavior like this. Okay? So that is some sort of a behavior in time. I do not characterize, we are not going to deal at this moment with this behavior, but we would like to be able also to deal with this type of behavior, which is some sort of irregular behavior. But in order to be able to analyze this type of irregular behavior, first we would like to start with regular behavior. That always has been in the universities, this approach. We start from simple and then proceed to more complex. Because later we will learn that complex behavior can be reduced to big collection of simple behaviors. Okay, now these systems these variations that I depicted, you may try to reproduce it somehow, but main thing is in this behavior that there is some part or some piece here that starts in this point when this W of t crosses the horizontal axis, and until it crosses second time this horizontal axis. And then this pattern continues or reproduces itself second time and third time and many times. Okay? So in this particular case, we talk about vibratory motion that is periodic. Okay? Then if the vibratory motion is periodic, the system repeats its motion at equal time intervals. So it's very simple. That is what happens. At equal time intervals, the system comes back to the same situation. This is not unlike the fact that today, for example, you again came back to go into the cycle of studying for a semester. Okay? So from the beginning to the end, and from the beginning to the end, and within these several years, we are in sort of vibratory motion of acquiring knowledge. And later we say to you, you know enough to go ahead and earn money and help the humankind. Okay, now we would like to ask them, we can say that if it repeats itself, say, in time interval t, then naturally it also repeats in time interval 2t. What I mean is, this picture is repeating itself. But if I will take picture from here until here, it also repeats itself. So that means that because picture is repeating itself, say from this time till infinity, that means that we can identify various types of intervals in which this repetition takes place. And between these various time intervals, there is a minimum time required for the system to repeat its motion. So minimum time is this t. Okay? Because if I reduce some time, so part of this t, say for example to t over half, then on the left behavior is different than on the right, so it is not repeating. So minimum time interval is capital T in this particular case. Minimum time interval required for the system to repeat its motion is called the period and denoted as T, capital T, which is the time to complete one cycle of motion. And we just say, so there is some function, f of t. We say that this property is f of t plus capital T equals f of t. That is actually the demand of periodicity. Now, paying attention that I will write down here. F, as we said, f of t plus capital T equals f of t. But it is also naturally correct that if I add here t here, t plus 2t equals f of t plus t, capital T, and equals f of t. So 2t is also an interval in which and 3t and 4t, etc., because this picture continues till infinity. So not only what happens in t is repeating itself, but also this bigger picture repeats itself, and 3 times bigger picture. But period, 2t is not period. Just 1t is a period. Okay. So what I want to impress you is that we have to find minimum time interval upon which is later being reproduced ad infinitum. Okay? So that is a period. Now there is a frequency also. Frequency is a number of times that the motion repeats itself per unit time. Say, for example, if from here to here time is 1 minute, then system repeated itself 2 times in 1 minute. So we are interested, how many times does the system repeat itself in a unit time, say in 1 second or in 1 minute or in 1 hour or etc. So that is of interest to us. Why? Because this talks about frequency. Frequency is a number of times that the motion repeats itself per unit time. So these are actually characteristics because how, okay, let me show you here. So imagine we have two motions. And so here is like this. So that imagine that they are all on the same level, etc. Now here is like this. So here, naturally, in per unit time, system repeats itself more times than here. So we would say that frequency in the first case is greater than in the second. That is important. This frequency is important because we can distinguish this picture from this picture. Okay? Or we can say differently. We can say that every time that frequency is bigger, what happens with the period? Period is smaller. Because more frequency means more repetitions, and that means that it takes smaller time to repeat itself. Now, so we have these periodic motions, but amongst periodic motions, there is a simplest possible motion. And that simplest possible motion is sinusoidal motion. But before that, we will show this. For example, this picture is electrocardiogram. I mean, of the live human being. Okay. As you see in electrocardiogram, we have a variation of pressure which is periodic or quasi-periodic, etc. Then systems that we will be analyzing from this point of view. So we will be very much interested in finding periods and frequencies. Why is it important? Why it is important to find frequency or periods? Why do I need this period? It's some characteristic of the system. Why do I need this? For example, it turns out that when industrial building of bridges started around the world, then, as you know, soldiers would march through one place to another place, and they also march through the bridges. And they are marching in unison. It turns out that some of the bridges collapsed. So how it is possible? I mean, the soldiers are not huge soldiers who came from aliens from another space, and they are so big that suddenly this bridge collapses. What happened is that the frequency of their change or of their steps coincided with the inner frequency of the bridge. And this system, as we say, came into resonance. And it turns out that when there is a system that has its own frequencies, and you use the force that has the same frequency, suddenly the displacements go to infinity or nearly to infinity, and system collapses. Stresses are very little, and displacements are very little. I think that everything is just okay. System should be standing there forever and ever. However, just one group of soldiers passes through it and system collapses. Naturally, we don't deal with this. We may say, okay, in this bridge, so we will not allow soldiers to pass. Or we can say we are asking soldiers not to pass in unison. They get freedom. Actually, nowadays, when soldiers are passing through any bridge, they are told not to walk in unison. They just walk as they want. Then there is this aperiodicity introduced, etc. But very often, this resonance phenomenon just brings many structures, extremely many structures, to collapse. So frequency is very important characteristic. Okay, now when we talk about vibrations, what kind of vibrations could be? So vibrations could be, characterized. Let us characterize these vibrations. First of all, according to the number of degrees of freedom. Okay, you may want to write. So characterization according to the number of degrees of freedom means single degree of freedom system. What is a single degree of freedom system? This is a system that can be characterized, whose behavior can be characterized by a single coordinate, just one coordinate only. Just if I know, for example, x of t, then I know where the system is. Then there could be multi-degrees of freedom systems. Multi-degree of freedom system is a system which has number of degrees that is finite, but it is bigger than one. So it could be 2 degrees of freedom, 3 degrees, etc., 27 degrees of freedom system. Or, for example, in modern analysis of finite elements, almost every, big structure is having maybe 1,000,000 degrees of freedom system, etc. Million or millions. This book. Yeah, this book is also extremely good. I did mention it. Maghreb and Balachandran. It's a very good book. Then continuous systems. These are systems with infinite degrees of freedom system. We need infinite, we need to know situation of infinite amount of points in order to know this. So for example, let me bring an example. So 1 degree of freedom system. So that could be like a concentrated mass, and say this is some spring, and it vibrates, so this is a concentrated point mass. So what I need is to know this coordinate x, and this vibrates like here and there. If I know x of t, then I know what happens with this system at any time t. Okay, 2 degrees of freedom system is also very easy to imagine. So that is M1, M2, for example, like this. So I need to know what happens with this x1 of t and with this x2 of t. Imagine in the beginning that is where they are. What happens then with the time in the future? It's 2 degrees of freedom system. And then I can actually have many such masses. Okay? For example, string with raisins. You can imagine string which has, say, 10 raisins. So then in order to describe this string with 10 raisins, say string has no mass, but there are 10 raisins that are concentrated masses. So I need 10 coordinates. I need to know where the first raisin is, where second raisin is, etc., etc. Now, for the beam, however, let us consider this beam. Or a bridge, if you want. Imagine a bridge. Then I need actually, look, in order to find the displacement, I need to know this function. That means that I need to know where this point is, and I need to know where this point is, where this point is, where this point is. How many points do I have? I have infinite amount of points on the axis of the beam. So this beam is infinite degree of freedom system. Beam certainly is not a raisin on the string. By the way, we are building our theory starting from extremely simple considerations. So at any time you have any questions, so please ask this question. please ask why. Okay, you can stop me at any time, ask me any question, whether it's why or why not, or how, that is, I think, not correct, or I have another input, I disagree or I agree. Any input, you have to stop me, and I will, for the benefit of those who are taking this course by feet, the only thing is the difference between regular course and this, that I will have to repeat the question. Otherwise, I do not hear you speaking. But once you are asking, I will repeat the question and I will try to answer. Okay? So please stop me at any time that you want. Then second is types of vibration. Okay, so types of vibration. Types of vibration could be free vibrations. Free vibrations means without excitation, there is no loading acting upon the system. Second could be forced vibration. Forced vibration is when there is a load acting upon the system. There is some loading, and system vibrates still. Now, when we talk about forced, there could be some transient state. What is a transient state? Imagine we take a structure and we are implying some force, some impact on the structure. It turns out that response later will be different than immediate response. So there is some transient behavior. There is something that in the beginning response is one, but later response changes. That is like in human relationships. You say someone to someone else, and there is some response, immediate response, but later maybe this response is totally different. Okay, whether it is positive or negative. Okay, so with time this memory fades maybe, or maybe our outlook changes, so we are responding differently to the same event. So the same happens with the system. These vibration systems are behaving very much like human beings. Then kinds of vibration. Now when we talk about vibrations, infinite degree of freedom system. So there could be longitudinal vibrations of beams. That is the first type of vibrations ever considered in the world. That was done first by Lagrange. Torsional vibrations of shafts. Transverse vibrations of beams. Vibrations actually, it seems to me, if I may say, but this is a biased opinion that I have, is the most interesting actually subject in the curriculum of engineer. And it is unfortunate that vibrations are not a required course, so to say, in every place in engineering. It is so in some universities, like MIT demands everyone to study vibrations, actually 2 vibration courses. Transverse vibrations of beams, etc., plates, shells, etc. Now, methods of solution. There are 2. Okay, that is very important to understand that there could be different methods of solutions, because usually, say in the university, we are actually spoiling our students by the fact that we consider only exact methods of solution. We are actually somehow miseducating our students, because every problem that we give, it can be solved exactly. We don't tell every student until now that, okay, there is this problem, but we cannot solve it exactly. I don't know how to solve it. Not only I don't know, but there is no one in the world who knows how to solve the problem exactly. So suddenly, vibration is I would say, more humble approach to what is happening in the world, because we say we cannot solve this problem exactly. But this happens very often, actually. There is nearly no system which does not vibrate. So actually, every system that you will be encountering in the real world cannot be solved exactly. Okay, so what we did in the university, we just provided you a taste. Okay, like for example, you go to a restaurant and they gave you a sample. So you try the sample. Then if you like the sample, you come in. Okay, but what you are eating inside probably will not be exactly the sample. So that is, we gave you only the samples. In the university for 4 years, you got only samples. But real life is very different, from that sense. In the sense that in real life, we are mostly 90%, not 9, maybe 95%, we are using approximate methods of analysis, because problem is too complex to be able, this is not a beam on, not 1 degree of freedom system, or not beam that is simply supported at 2 ends, and there is a load in the middle. Oh, that is a problem that we solve in strength of materials, or this is not a circuit problem that can be analyzed, say, by very simple electrical engineering methods, etc. So we need to use approximate methods. So most famous of approximate methods is, of course, finite element method. So therefore, I would recommend in the future to take, if you would like to be in engineering, to take finite element method course. It is a mostly used method in analysis. However, beautiful thing is that without knowing all these exact methods that you could have said, look, please, if we are using only finite element method more or less at the end, why did I need this 4-year education? They should have given me finite element methods in the first semester, and we would have finished it. Yes, but in order to understand this finite element method, we need this 4-year instruction at least, in order to, first of all, recognize that this problem cannot be solved, or maybe could be approximate, or maybe could be approached somehow. And here I did talk about various methods. So there is finite difference method also is very, very famous method. I hope it is taught in applications, computer method applications. I hope that it is taught there, but there are other methods. Okay, so now we talk about these periods. Okay, so what we could do is actually, look please, we can do some experiment more or less here. So when we talk about vibrations, we can take some small, so this is a frame, and here I'm pushing the paper, and this thing has a sand, and we are vibrating it. So we gave him a push, and it goes like this. The system goes like this. At this time, I'm actually pushing the sheet of paper. And imagine that this sheet of paper has it's an oily paper, so that once sand is attached to it, it stays there. So that later I can actually show this picture that I got as a result of these vibrations. So actually we caught the vibration of this system in 2 directions here in this picture. So this is a small a, or it is called amplitude. This is a maximum displacement. So this is, so to say, static behavior. If it would stand still here in the middle, then that is on this line, system would be aligned at this horizontal line. But then we start from here, and that is how system behaves. And period is identified here as, say, I took any point, and then I'm finding where this picture is repeating itself. So I have to, from this point, pass on straight line, and wherever the straight line is crossing this trajectory of vibrations, is this picture ending. and then it repeats itself. So this is a period. Okay, so very easy to conduct such an experiment. I'm not assigning you to do it at home. So we can actually then look. Imagine that speed of my movement was 10 centimeters per second. Imagine I'm just measuring it after 1 second. How many centimeters did I push this paper? It's very easy to measure. Or how many centimeters did I push it in 2 seconds? So someone else can do it, or I can do it myself. So then I can say, imagine that this velocity or my speed of moving the paper is constant. So 10 centimeters per second. That means that 1 centimeter I'm pushing in 0.1 seconds. Now, 002. So let us see the period. Period is, of course, this distance, but it is also period between point O and point O2. That is also, best is, of course, to see where it intersects with the horizontal line. Distance between O and O2. So I can measure this distance. So this distance is 16 centimeters. So that means that in order to get from O to O2, I need 1.6 seconds. Okay, because it's 16 centimeters. 1 centimeter is 0.1 seconds. So I need 1.6 seconds. Period equals 1.6 seconds. That is how I found the period. I found that in this system, vibration were 1.6 seconds. In 1.6 seconds, system's behavior is repeating itself. That is how we found it. Now imagine that we have different pictures here. We have 2 pictures. Okay. Okay. So this is x of t, and this is also these 2 pictures, A and B. So we see that maximum from 0 to, so the greatest value that x of t can take is called amplitude. So this distance is amplitude. So amplitude here is bigger than amplitude here. Okay, so this is A1, this is A2. By the way, this is A2. Here I don't see, if you see, I don't see myself very well. But let me enlarge and maybe we will see that. Yeah, we see that there is 2. At least I tried to write 2. Okay, as we see here, so periods, are the same. This T1 equals T2. So periods are the same, amplitudes are different. Why periods are the same? Because in the same points we have intersection with axis, so therefore periods should be the same. Now here, second picture, I would like you to make note of it. And maybe try to repeat it. So in the first part, period equals T1. Amplitudes are different. Oh, excuse me, A1 equals A2 I wrote. So amplitudes are the same. Periods are different. So what I tried to do is, I tried to make the same picture repeat 5 times itself within this T1 period of the first vibration. That is what I tried to make. So let me count. So this is 1, 2, 3, 4, 5. And that is where I am. 5 times. T1. has a period which is 5 times t2. Say, for example, we can have examples. Okay. Say, okay, for example, when we talk about some vibration, so beam is a straight beam, but it can vibrate like this. Look, please. That means that every point of the beam is on one side of the axis. So all of them are positive. All points are positive. Only the end points are connected. Like that could be a bridge, for example. Because in the bridge, naturally the end points, place where you enter the bridge and place where you depart from the bridge, are on the same level, and they are connected with other structure. So these points are constant or connected. Now, first vibration mode, now this bridge can vibrate in various modes. That is not detectable visually, naturally. One possible vibration is that all points are on one side of the horizontal line. So that is like first mode. Or we can say there is no 0 point inside. There are zeros only at the ends, on the boundaries. But in the middle, anywhere, there is no 0 there. So that is first mode. That is easiest to excite as if, because all points go in one direction. Okay? And now second mode is more difficult or different. That is like some points are on the positive side, some points are on the negative side. One is on one side, others are on the other side. That is like in elections, there is one, people are voting for one candidate, the others for another candidate. So there is a split as if in between these points. That is more difficult to realize naturally, such a system. So, for example, in this case, that is 440 hertz, 880 hertz. Now, sometimes it happens that there are, so this has one 0 point. This 0 point is called node, N-O-D-E, node. This point is called node. Here, no inner nodes, you may want to write. This is also, of course, a node because this is 0, but we better talk about inner. No inner nodes here. One inner node. Two inner nodes, etc. So, for example, just for us to know, airplane wings have many vibration modes, so vibration behavior. So usual say frequencies are say 1.5 hertz, or period is 2/3 of the second. So say wings vibrate in such a manner that in less than 1 second, actually this periodic vibration takes place. Less than 1 second. Now, if you go to Boston, I recommend you to visit John Hancock Building, just you can see from outside. So in John Hancock Building, actually system is vibrating and with period of 7 seconds. Okay? In wind situation, that is more visible naturally than in regular situations. Now the Earth it turns out, is a vibratory system also. It has various vibration modes or vibration behaviors. And reality, what happens is superimposition of various things. So it behaves like a musical instrument. So for example, there is these points where we are all distanced from each other. So we are all like imagine a balloon that becomes bigger. Then it goes down. So there is vibration. This is called breathing mode. Earth as if is breathing. And it turns out that this breathing period is not very big. It's 20 minutes. Every 20 minutes, you can just see Earth, just in 20 minutes, Earth breathes in or out. Period is 20 minutes. It's not a very big time. Then there is also something like that when system suddenly it becomes elliptic. I mean, not that it was not elliptic from the beginning, but the whole, say, these two parts are getting closer, but parts here are getting away from each other. So that is another possibility of vibration of the Earth, upon which this lecture, it seems to me, is being conducted. Okay, so this is called microcentury. Okay, and look, this takes place, in, I'll tell you, 52,560 minutes. This period of vibration of this kind, or 100 years. So we probably, each of us, will live about a bit more than 100 years. So that means that in our lifetime, this will be just vibrating in this form only once. Okay, we will be just catching only one period, or maybe a bit more. Maybe in 10 years there will be some life-prolonging medications in such a manner. Maybe we will live just 200 years, maybe just 2 periods. So next time, for the new year, you can say to your friends, I wish you to live 2 microcenturies. So in order us to catch, so to say, 2 vibration modes of the Earth. Next New Year actually is a Chinese New Year coming on February 25th, so you know what to tell to your friends. So this is number of degrees of freedom. Say, number of degrees, okay, beam model. So imagine this, we talk about Apollo, Saturn V space vehicle. So it's a long time ago even. So beam model sometimes could be, look, this is, do you remember I talked about raisins on the string? So actually engineers are approximating Apollo like 30 raisins on the string, nothing else. Finite element method says, thank you very much for information about Apollo. I don't care about this. For me, Apollo is 30 raisins on the string. Okay, that of course should be done by a computer. Otherwise, you cannot deal even with this. Or if we want better approximation, so then it is, say, 120 degrees of freedom system. We see a bit more details here and here. Then 400 degrees of freedom system. So analysis is done only for the half part. Why? Because there is a symmetry. That is a, say, rotationally symmetric system. Then more difficult 3-dimensional model, that is 300 degrees of freedom system, etc. All these models are very different from each other. Analysis is different, mathematics is different, etc. We would like to just touch at least a bit each of these in this course. And okay, there are of course some experiments done. Okay, dynamical testing of structures. Okay, so for example, ground vibration testing of 1/4 scale model of the space shuttle orbiter vehicle, etc. So that is a long time ago, done in 1977. I did some research for space shuttle about 10 years ago in order to design its weather protection systems. So there we used big number of finite element models, etc. Why experiment? You can say, why do we need experiments? Because theory still is an approximation. We are making assumptions. And these assumptions, we don't know whether they are correct, not correct, etc. We would like to conduct an experiment and see how our modeling is catching with reality. So on one hand, there are models. On the other hand, there is an experiment. So from this point of view, His Excellency is an experiment. Please write down this expression if you don't mind. His Excellency's experiment is deciding which theory to be adopted. Okay? Experiment is a king. This was not right. So many non-writing things. So actually we need these two things. Theories, and of course we need computers, computer analysis. So we need three things actually. Of course there is a big need in the engineer himself or herself. So an engineer that uses theories, computer analysis, together with His Excellency's experiment, which decides, which is actually has the final say. Final say. You are on the right direction, maybe you are making a big mistake, maybe it is not so, we have to change things, etc. Okay. So we will talk about simplest things. And simplest thing is like this. Look, please. There is this point. Imagine that there is a point mass. That is an approximation. Mass is concentrated into a point. So this is like a mass was on the diet, and it became a point. So that is what has happened. Okay? For the mass, it's very easy to do a diet. And it is a point. Now I have now this point can move only on this line, on OX line. This point has 1 degree of freedom. Why it has 1 degree of freedom? If I know the distance from the origin to point P, this is x. Then I know everything about this point. I know it has a mass m, and I know the distance is x. So I know everything. I know the location of this point. This is like a dog with a leash, okay? This dog is moving around, but the distance, maximum distance to the person who is holding is equal to the length of the rope, so to say. Okay, so now we will consider, we are talking about periodic motion, is it right? In vibrations, we are interested with periodicity, something that varies in time periodically. So, simplest thing is OP, or this distance OP, equals x of t, equals capital X times cosine omega t. What does it mean? Capital X cosine omega t. That means that maximum value from point O can be big X. Okay? It can get to this point, and it can get to the left-hand side to minus capital X, because cosine omega t varies between -1 to +1. So this point is actually like moving here and then back to minus x and again back to x, etc. That is how it moves. Nothing else. Now, So this can be written as OP equals capital X times cosine omega t. And what is t? T is time. Omega is some constant. Capital X is also a constant. So now we would like to analyze this system. What is this system's period, frequency, etc. that we would like to know. This is simplest possible periodic motion. Okay? Now, yes. What is a period? Period is, for example, if I had just cosine t, imagine I had cosine t, forget now omega. Imagine omega equals 1. If omega, write down please, omega equals 1. Consider a simplest case, omega equals 1. We will do later when omega is not 1. If omega equals 1, then we would like to find the period. What is a period? Period is such a minimum number, capital T, that cosine small t plus capital T equals cosine small t. It's very simple. Okay, about cosine functions we know a lot. We know that such a number is 2 pi. Cosine t plus 2 pi equals cosine t. So we are concluding that for this function, cosine t has a period which is 2 pi. Okay, 2 pi radians. Period of function cosine t equals 2 pi. Now let us deal with we don't have cosine t, we have cosine of omega t. Omega is any number. Omega is a constant. Omega is not necessarily 1. It could be 1 or 2 or 3 or 1.5, 1.75, etc. Anything. Okay. So now I know that cosine function has cosine omega t plus 2 pi equals cosine omega t. We know that 2 pi is something that could be added to the argument, and the function will not change itself. Okay, so that is trivial. What I wrote here is trivial. First line is trivial. Second line is less trivial. Because in the second line, I say from this trivial observation, I will take omega out of this parenthesis. I will get small t plus 2 pi over omega. Because I took out omega. Omega are canceling each other. I would get them when I multiply 2 pi. Okay. And now I would like to fit this definition. What is period? Period is something that once I will add it to small t, the function will not change. Cosine omega t plus capital T equals cosine omega t. That is what period is. So from here I find that period equals 2 pi divided by omega. So this makes sense. When omega equaled 1, the period was 2 pi. You may want to write. When omega is not 1, period equals 2 pi divided by omega. So it makes sense. Whole thing makes sense.
All of these are established from identities?
Say it again?
All of these are established from identities, trigonometric identities?
Yeah, because of trigonometry. Because of trigonometry. Because look, please, cosine function, okay, I can actually write down. Thank you. The student is asking whether or not I got this from trigonometric identities, and I answered yes. For example, let us take cosine t plus capital T equals cosine t. Yes, that is what we found the period. And I said cosine t plus 2 pi equals cosine t. Let us consider this. This is cosine of sum. Cosine of t plus 2 pi equals cosine t times cosine 2 pi minus sine t sine 2 pi. Now, this sine of 2 pi equals 0. Okay? Cosine of 2 pi equals 1. So I got cosine t plus 2 pi equals cosine t. Okay? So I got it from trigonometric identities. The same I can do with another one if you want. I can do immediately. So I use this knowledge that cosine function has actually repeats itself after 2 pi radians. And that means that cosine t has a period of 2 pi. Analogously, I can do with the rest, say cosine omega t plus 2 pi. So this equals, of course, cosine omega t cosine 2 pi minus sine omega t sine 2 pi. Sine of 2 pi equals 0. Cosine of 2 pi equals 1. So I get that cosine omega t plus 2 pi equals cosine omega t. Okay. Please ask questions, because it's very, very important that we are on the same wavelength, so to say, especially that we talk about vibrations. Okay, so period then of cosine omega t equals 2 pi divided by omega. Now, frequency is number of oscillations per unit time. So therefore, it equals 1 divided by the period. That is a frequency. How many times in 1 unit of time I will have repetitions? So it is 1 divided by t. That is the number of times. So it is a frequency. But that means that it is reciprocal to what I wrote here. So it is omega divided by 2 pi. 1 divided by period, 1 divided by 2 pi over omega is omega divided by 2 pi. And that is cycles per second. So that means these were the cycles per 1 unit time per 1 second. This is given a name Hertz. Hertz. Hertz is a German engineer, famous German engineer, in whose honor actually this frequency was named. This happens analogously to, so to say, Lord Newton. If you remember, there is a legend according to which Sir Isaac Newton found the gravitation law once an apple fell on his head. So usually the weight of the apple is 1 unit, and it is 1 Newton. So therefore, apple's weight was taken as Newton. So Newton will be should be very happy every single day if he gets communicated how many times his name is used or sometimes misused by students, professors, engineers, etc., etc. So this is Hertz. Hertz is a German engineer. So we are using Hertz, or if you don't like, the names, so cycle per second. Cycle per second is Hertz. Okay? Omega is called itself circular frequency. So look, there is a notion of frequency. Frequency cycles per second. But omega itself is also connected with frequency. It's just called circular frequency, measured in radian per second. So small omega is circular frequency measured in radians per second. Any questions? By the way, usually we say, now it is simple, but later will be complicated. No, this course is not like this. Now it's simple, and at every point of this course, it will remain simple. We will deal with complex matters, but everything will be extremely simple. I'm trying always to explain things in the simplest possible way. Okay? So everything will always be simple. That I can promise you. Okay, now we will do some small exercises. Oh, I pressed somewhere.
Press the power button.
Oh, power button. Here.
No, on the overhead.
Oh, can you come here? Can you come and maybe they are there, or maybe. Oh, sorry. Oh, this one. Okay, thank you. Oh, thank you. So the question is like this. Now we will deal with extremely simple question. And this is as follows. I have now two periodic motions. Two periodic motions. What happens with the resulting motion? Okay. If I have just cosine omega t, I know how to solve the problem. That's not a big problem. Now imagine I have two functions that have various periods. Okay, imagine x1 of t. So we will deal with very simple class exercise now. By the way, today I'm not giving you any homework, so that will be the only exercise, and we will just start it. So I will just give you food for thought for the next time. x1t is a1 cosine omega 1t plus phi1, or phi1. x2t is a2 cosine omega 2t plus phi2. So I have one periodic motion with circular frequency omega 1. Then I have second motion with circular frequency omega 2. So each of them separately are periodic. What happens if I'm superimposing these two periodic functions? Okay? Two periodic functions are marrying each other. So the question is, what happens with the resulting motion? Is it periodic? And when and how, etc. So, for example, look please. Imagine that one function has a period 1 over 300 seconds. So that means that 1 over 300 seconds, first motion repeats itself. Now, second motion repeats itself 1 over 200 seconds. What happens with the motion that is a superimposition of these two motions? I would like to ask you. You can talk to each other, by the way. Therefore, next time, it is nice to sit next to someone so that you can discuss with him or her a topic under consideration. It's always good to have some input from someone. So my question is, period of one motion is 1/300th of the second, and period of the second motion is 1/200th of the second. Do you want to give me any input or any thoughts, or if you want? Yeah, frequencies are different, but I'm not asking you frequencies. I'm asking you period. Pay attention. I ask you periods. I gave you periods of input quantities, and I would like to period of output quantity. Okay, at this moment we would like to finish our lecture because I see zeros over there, and that means that lecture is over and it is not being recorded. Thank you. I was told that in Japanese parliament, but I did not check that, and I feel uncomfortable. Every time I was there, I felt uncomfortable to ask.